chemistry 1, sir.
Sir, so I wrote a mock test today, sir.
Okay.
Like it was just before class started, sir. I mean,
Okay.
yeah, the 11 o'clock class started. So
Okay.
I started writing at 10, and by 10:30, by 11:30, I just got reminded that there was class. So I left the entire math section, and
Okay.
I rushed some of the chemistry questions, sir. I ended up getting 78, I think, sir.
78. Okay, fine. So that's what, like more like you have almost like 2-3 days more tests you write. At least make sure that at least write 6 tests, minimum of 5 tests before your exam. Like
I'll
that.
definitely write that, sir. Even after this class, I'll take a 30 minutes break, eat, and then I'm gonna sit and write, sir.
Yeah, that's better. Right. So
This is
make
I found
five
this
tests.
site, sir, that basically does all the evaluation for yourself. Like it
That's
just
what
gives
is
you.
given in the software. No, Epsilon people gave you software. That's that.
But that software only has two tests, sir.
Oh, only 2 tests
And I
are
wrote
there.
both of them. Yes, sir.
Okay, okay, okay. Did you get to know the answers like
Yeah,
analysis part?
yeah. And analysis was there, sir. That's the advantage.
Okay, analysis was there. That's okay, okay, right. See, like if at all you want, we can even I can even prepare a mock test and give you like we can put it in the Epsilon's app, and then actually you'll be able to go through it and get the analysis also. That's the best part. You'll be able to get the analysis also. Analysis means which area of particular like in chemistry, which area that would be difficult. But overall, actually, some kind of analysis can be built in the Epsilon tablets. Right. So in the software, whatever they're giving, are they especially telling it for
Yes, sir.
specific
Yes, sir.
areas?
Yeah, they are.
Okay, okay. Like
Basically,
that
there's
way.
a two tests for mains and then one bit side mock test, sir.
Okay, okay. See, there is a thing called as Imbibe. I think you know about it,
Yes, sir.
right?
That's what I wrote today morning.
Oh yeah, and see, Imbibe. The thing is, Imbibe questions will be very tough in the mock exams. Right. With that, you don't decide. But again, it's a very good platform. Like in the sense that the quality of questions, also as you said, the analysis part is actually pretty good. You can actually do it.
Sir, you
So
have to pay
Imbibe,
for that thing, sir.
yes, yes, it's worth it. It's worth it. I don't know how much it will be for one test series, held entire test series.
I don't know, sir. It showed some coins, sir. So I just looked at the marks and left it.
Okay. There are a lot of online mock tests like this with good analysis. Again, like even though you don't have the analysis, at least you can do the analysis on your own, but it should be able to give you the solutions. That's the best.
Yes, sir.
That's it. Right. That if you have, at least you can make by yourself. Yeah, Imbibe is one. Check whether Resonance has started any test series or even Allen test series is good. Right.
Okay, sir. I'll check, sir.
Those are all the things. But
Sir,
like
even the NTA
yeah.
has its own test thing, sir. But I haven't tried it. I haven't. Does it give an analysis?
The sample they give analysis also,
No, I
mock
don't know. I'm
tests.
asking, sir. So it has like a lot of papers, sir. All the previous year papers is there.
இல்ல அதுல அனாலிசிஸ் இல்லைன்னு நினைக்கிறேன் அந்த ஒன்லி அந்த
Okay.
கொஸ்டின் பேப்பர் அந்த அபியாஸ் அந்த
Oh, okay. See, Pranav was writing. That's why.
Okay. A lot of options actually. Tests there are a lot of options, but you have to pay money. Without that, you'll not be able to get anything out of it. You'll just maybe get the question paper. Right? You
Yes,
have
sir.
to.
Question paper and marks you get without paying anything, sir.
That's what that you will get.
No
But
detail in it.
analysis and then solutions for all these things you might have.
Yes, sir. Solutions is not there.
Yeah. Anyways, if at all you want, we can even prepare one. Like maybe not now, but once you have for your first attempt, maybe we have various number of days. It's not possible. But for the next attempt or not, we can like say weekly two times. Like we can only conduct a mock test. Like
Yes, sir. Try it. Please do that, sir.
we'll do it. I'll discuss with Raghav and Nitin. Like they say, they will see what they say. We'll
So
decide.
weekly once also is fine, sir. But we
Yeah. When is your board exams? When is it starting?
May 4th, I think, sir.
Oh, you have your board exams only by May.
But March first week we have practical, sir, and we'll be like after the second we write our JEE mains for the first time, we'll be bombarded with a lot of practical work, sir.
Okay, fine. So at least that will maybe go for full March. April again you'll be free. Like again, only May you have exams.
March, sir. It will go till March first week only, sir.
That's what. So almost entire of March and April you'll be free. So
Yes, sir.
Like see, when we conducted crash course, last year, the same period we started. So it was like daily they'll have 4.5 hours or 5 hours of class, and then after the end of the each session they'll write a test, physics, chemistry, math together on the topics which was taught, or at least the previous day's class. How feasible that we were doing, and at the end we gave them around like 10 mock tests from our side, all in the app. They did it. I think something like that can be possible for you also. Why not? But we'll not be able to go for minor test series. Minor test series also actually we can do. It's not a big deal. Minor test series, this thing, say 2-3 chapters put together. Maybe for your next attempt, we'll be able to do that. Say start with 2-3 chapters, complete everything, and then say one minor, one part test. Part test where, for example, in chemistry we can do only physical 11th and 12th, only organic 11th and 12th, only inorganic 11th and 12th. So 3 papers, and then say some mock test, full portions mock test. So that can be done. We'll see. I'll speak about it to them. Right. But you finish your first exam and let me know how was it. We'll plan. Okay. Fine. So we'll continue. So there's just a small part left. How many people are there? Only 2 of you. Okay, fine. So we'll just complete the small part which is there in metallurgy. Where is it? Yeah. Okay. So we have to see what is this blast furnace, right? So in blast furnace, this is how it's actually look actually. Bear with my diagram, but this is almost how it will look. Okay, so here only I'll supply your temperature, your heat. Okay, so through this you will have various openings here and all to just let air come in, say, and then through this air and oxygen, and through this you give the slag, and then you give the ore plus the gangue, right? And also you give the coke, that is carbon and carbon monoxide, a mixture of that you give, right? So all of these things, and eventually you'll have, so basically in this you'll have different temperature zones. Is it not? This entire thing can be divided into some temperature zones. Temperature zones, is obviously you're starting, you're heating. This will be a very big thing. Like assume that whatever room you're in, right? That big sized furnace it will be, right? So you will be heating it at the bottom, right? So obviously at the bottom ranges, you will feel that obviously there's going to be higher temperature, and as you move up and up and up, the temperature keeps reducing, right? Say I can just give you a picture here. It will be in the bottom range. It will be around 2170 Kelvin, and say I have in the topmost layer can almost have 523 Kelvin, right? So you'll have all the intermediate temperatures from this to this as we go linearly higher and higher. Okay, so we saw Elingham diagram, right? So from the Elingham diagram, I'll be able to actually see, obviously you saw it is delta, the enthalpy of, not enthalpy, the gives the energy of formation with respect to temperature. That was the plot, Elingham diagram. So what it tells you is at a particular temperature, I'll be able to choose a suitable reducing agent, isn't it? So what is going to happen is at different temperature zones, according to which delta G is going to be negative, or which combination of reaction is going to give me a negative value of delta G, right? So different temperature zones are going to have different reactions happening, right? So you just have to know what are the reactions happening at different temperature zones. That's why I wanted to talk to you about this. Okay. Fine. So we have different zones. So like the diagram is not important. I can just rub this off, right? So you can, okay, now order other tests. You not slag, this is the flux, right? The flux you add, the ore plus gang, the carbon, say, oh, this is basically done for iron ores. Basically, when I say ore, it is some form of iron ore. Okay, right? What else you need to know? Yeah, that's it. That would be fine. Okay, so we'll see what are all the different reactions happening in different zones of temperatures. Yeah,
I didn't note down what flux and slag are. So.
Oh, nothing. So basically, this gang, right? This gang particles are not that easy to remove, right? So in order for me to remove them little easily, if I convert them into different form, I'll be able to remove them easily, right? So what I do is to convert them into a different form, I add something called as flux to the gang, right? And these two will form together called as slag, and this can be easily removed. Okay, so flux reacts with gang to form slag, which can be easily removed. Again, you can, depending on what type of gang you have two different types of gang: acidic gang or basic gang. Same way you have acidic flux and basic flux.
Yes,
right?
That time.
So,
yes.
So depending on that, you will choose what you have to choose, and eventually the slag will be. Okay.
Okay, sir. Thanks.
Right. So we'll see what are all the reactions happening. Right. Say first one, the lower temperature zone is what is called as zone of combustion. So this happens in around temperatures of 2170 Kelvin, right? So you will see that carbon will react with oxygen to form CO2. Okay, right? So this will be a highly exothermic reaction, right? So anyways, now next second zone is what is called as zone of heat absorption. Right? So in the zone of heat absorption, what you're going to see is this reaction, which is CO2 plus carbon is going to form CO. Now you see enthalpy of this reaction is plus 163.2 kilojoules. So what you have to understand is in this temperature zone, in this zone of temperature, this reaction needs energy. You can see it's an endothermic chemical reaction happening, right? So this is going to absorb the energy and make sure that the reaction is going to happen. This reaction is going to happen. Okay, right? So, and this happens between the temperature zone, if you ask me, it is around 1473 Kelvin to 1673 Kelvin. Under between these temperatures, this reaction would happen. Okay, next is the third zone, a zone of slag formation. Right, so you can understand in this particular temperature zone, the slag is going to get formed. You know what is a slag, right? So this happens around 1123 Kelvin. This is almost in the middle of the blast furnace. Okay, right? So here you can see what are the reactions will happen. Say CaCO3 will form CaO plus CO2, right? And then this CaO is what is the flux molecule will react with SiO2, which is the gang molecule. This is the flux, right? Now you will be forming CaSiO3, which is the slag, right? Okay, so that's the third zone. Now you have the last zone, or last before zone. The fourth zone is zone of reduction. Right, basically this step you will be using after the oxidation process. Please understand that. Okay. Or sometimes oxidation and reduction to happen simultaneously. You go for this blast furnaces, but mainly you go for reduction because you're adding you can understand you're adding carbon and carbon monoxide. Those are going to act as reducing agents. Okay, so predominantly we use blast furnace for reduction purposes, but sometimes it is used for both oxidation and reduction purposes simultaneously. But predominantly, yes, it is used for reduction purposes. Okay, right. Fine. So in this zone only, the actual reaction what we want is going to happen, right? So there are. This is the temperature zone. I have around 500 to 900 Kelvin, and you see the different reactions happening here. So you have Fe2O3 reacting with carbon monoxide to form Fe3O4 plus what? Oh, CO2, right? And then say another reaction can be Fe2O3 plus CO gives FeO plus CO2, right? And then say Fe2O3 plus CO gives FeO plus CO2. Or at the last, you can have FeO.
Third are same, no, sir.
Oh, okay. What happened then? Oh, this is Fe3O4. Sorry. Right, this is Fe3O4 and this is Fe2O3. Okay, fine. Now this is fine. Right. So I have FeO plus CO is going to form Fe plus CO2. So you see, you got the ion here. Okay, right? So there you got the ion there, and there is another way also you'll be able to get it. Well, now you can see in all these cases in these temperature range. So what I understand is carbon monoxide is a better reducing agent. That's what I understood. Okay, so carbon monoxide to form carbon dioxide, that reaction is spontaneous. That's what I understand in this temperature zone, 500 to 900 Kelvin. Yes. Okay. Fine. One last reaction where carbon can also involve, right? So carbon can involve in this reaction. Fe2O3 plus C forms Fe plus CO2. Right? This happens exactly at the temperature of 1123 Kelvin. Okay. So it strictly speaking, it doesn't come under this zone, but still very close to that. 900 and 1150 are not so different. Right? Fine. So these are all, this is exactly what we need. So iron is what we need. Okay. Right. And the iron we get from here is called a special iron. What is it called as? It's called, one second. Okay, but there are different types of iron that will tell you. I don't know which one is got here. What is Augusta? Okay. Right. So I think whatever you get here is what is called as pig iron. The iron which you get from here, it's what is called as pig iron, right? Now this is little impure, right? So from this you will be able to form a more purer form of iron called cast iron, right? Now cast iron is what is used for your building purposes. The steel, I don't know, the what is it called as the beams or the columns which you use for your houses, or the ceiling which you use that in Tamil we say kambis, right? So those is what is cast iron, and this is also not that pure. It is almost like 97% pure. This is almost like 95% pure. And at last, the most purest form of iron is this what is called as wrought iron. Right now, wrought iron is almost 99% pure on the iron. Okay, right. So, but this is used for different for making magnets, super magnets, superconductors, all these things wrought iron is used for. Okay, right? So from the blast furnace, what you get is pig iron. It can be converted to cast iron and then to wrought iron. It's just different varieties of same iron, but just having different purity numbers, percentages. Okay, right? So this is what I wanted to tell you about yeah, blast furnace. Okay, right? So that's it. So we'll go for next solid state. Still only two of you. Oh, now Varun left. Okay, fine. Cool. We'll start with solid state. Okay, first question to you is, there are something called as crystal systems, and I have something called as Bravais lattices. Right. So the question is, what are these? How many of these are there, and what are these, and how many of them are there? I want you to tell me. So there's something called as crystal systems, right? And you have something called as lattice, or you also tell me what is this unit cell, right? Fine. Anyways, tell me, what are these? Okay, right. So when I say crystal systems, first what you have to understand is this something called as space lattice. Okay, right, fine. So when I say space lattice, assume that I have a solid. Okay, now this solid, what I'm trying to do is I am trying to say, if this is the solid, say, okay, assume that some part, this entire thing is a solid. Okay, now I am going to do equipartition here. Okay, what do you mean by equipartition is I am going to make something like this. I'm going to make horizontal lines and vertical lines. Okay, right? Assume this is in 3D. This is just a 2D picture, but assume I'm going to have lines coming here, going in and out also. Okay, right. So, so you see there are going to be meeting points, all these points. Okay, right? So like I am going to make sure so this entire arrangement is what is called a space lattice, right? So like what to say, equipartitioning the solid system into this small areas is what is called a space lattice, or entirely basically we talk about the structure. Okay, right. So you like remember this particular points are what are called as lattice points, right? So what do you mean by a lattice point? Let me tell you first. Okay, so it's like, I don't know whether you saw this, what is this movie, Interstellar, am I correct? Okay, so yeah, have you seen this movie Interstellar?
Yes, sir. Yes.
So the Interstellar, once you go inside, I think the black hole or whatever the portal, or I don't exactly remember the movie. So you will see that he will see different I don't know, incidents of his life which Jesus moves on when he walks and walks. There'll be a, I don't know, you will see horizontal lines, vertical lines everywhere. Wherever he sees, it's gonna be same. Do you remember that scene? Or is it the same movie which I'm talking? It's the same movie, Interstellar only, right? Yeah, it is
So
Interstellar
where he'll
only.
be looking at his daughter and all that. That's what he'll...
Correct. He'll be looking at his daughter, and wherever he looks, other than the picture, other than the what to say, the pictures he is seeing, everywhere, whatever he sees, it's going to be the same, right? So that is the analogy which I want to give you here. It is that kind of space, it is that kind of system where if you're going to stand here and look at your environment, observe it, right? Then you move here, then you observe the environment, right? You are actually not going to see any difference at all. Okay, that's what's the point. So, but if you have somewhere here or somewhere here, if it is not a lattice point, and if you look at it, maybe you will feel at different points, you will feel different environments surrounding you, right? So, but if you're going to stand at two different lattice points, or if you're going to stand at individual lattice points and check the environment around you, like, you are going to see that what to say, everything is around you is going to be same as all the points, all the lattice points you have. Okay, right. Fine. So from this, so this is what is the lattice. So where the lattice points are there, those are the points from which wherever, I mean, you see at different lattice points, whatever you see is going to be same, right? Or I can also tell that these are the points where I can have atoms or molecules or group of atoms. Okay, fine. Instead of calling them as molecules, I can call them as group of atoms, or it can be ions. Okay, depending on what solid it is, right? So even though they are not going to fit exactly in these lattice points, we'll adjust the lattice itself so that they will, like, these atoms or molecules or these ions, wherever it just exactly fits in these lattice points. Okay, right? So I hope you understand. Okay, now what I'm going to do is from the space lattice, right? From the space lattice, I am going to take the smallest unit out. But again, there's a condition. The condition is that smallest unit you take, right? And then if you replicate it, if you just make similar blocks, similar units, just pound over it, arrange it properly. If you do it properly, you should be able to get back the lattice, space lattice. That is the condition. Okay. So what I'm trying to tell you is that the smallest part which you take out of this lattice is going to be in such a way that when it replicates itself in all the three directions, should be able to bring back the lattice. Okay. Now that smallest portion you take is what is called as your unit cell. Okay, this smallest portion you take is what is called as your unit cell. So basically, the unit cell is the smallest part of the lattice, which when replicated in all the three directions will produce the entire lattice, space lattice. Okay, right, fine. So this, what to say, crystal systems, basically, we are going to see that this is kind of a unit cell. Okay, but so, or I can even call crystal systems or unit cells are actually different, right? So what I'm trying to tell you is, if you're going to make some shape out of a molecule, right? So, or in other words, you would have seen crystals, isn't it? So you will have, I don't know whether you have seen, like, one type of crystal, what you have seen will be cubic in shape, or you at least assume it to be a cube, or you see snow crystals. Snow crystal will be very pointed, right? Or say there'll be spikes, like one spike, second spike, something like that. So there are different kinds of crystals. Okay, so that types of crystals comes under crystal systems. Okay, now please understand, all these crystal systems are actually going to be either 8-edged or 6-edged. Now, but mostly it is only going to be 8-edged shapes, right? Now, how will you define these 8-edged shapes? Is very simple. These can be mathematically coordinated. How the shapes of different crystals would be can be mathematically predicted, right? So for example, you will have, I think this you have already studied, right? So whatever, if this is the, if I have to draw it first, I'll draw the thing properly. Okay, say this is my x-axis, this is my y-axis, this is my z-axis, x, y, and z. Yeah, okay, whatever, mutually perpendicular. Okay, right. So you see, whatever this is a cube which you see, but it might not be a cube depending on the conditions I'm going to tell you now. Right. So you see, there is a length here which makes with the x-axis. This cube or whichever the shape makes with the z-axis, and whichever makes with the y-axis. There are three lengths, and you see there are three angles also. Right. So based on, so these angles are what are called as alpha, beta, gamma, and the lengths are what are called as ABC, and the angles are what are called as alpha, beta, gamma. So in your book, you would have seen the conditions. If alpha equal to beta equal to gamma equal to 90 degrees, and if A is equal to B equal to C, you will get a cube, basically. Right. So like that, I can have 7 different crystal systems coming out depending on various changes in length and the changes in angle of ABC and alpha, beta, gamma. Okay, so rhombohedral, triclinic, monoclinic, triclinic, rhombohedral, simple cubic, hexagonal, right? What else? There's so many, right? Okay, there are at least 7 if you calculate. I mean, if you just count. Okay, fine. So in our these things, right? In our syllabus, we are not going to study about every crystal system. We will study only about simple cubic systems. We are not going to study about any of the systems. Okay, right? Simple cubic is basically a cube. That's it. That is only that system we are going to study. Okay. Now, but this simple cubic itself will have different unit cells, different types of unit cells, depending on where the lattice points are. Isn't that this simple cubic only? Right. But if I just mark these corners, or say if I'm going to put it some lattice points, I can have so many possibilities of putting a point where the atom can be present depending on the arrangement. Right. So depending on where the lattice point is, right, you will be able to get different unit cells for simple cubic itself. Right. So simple cubic, if you check simple cubic, you can have a simple what is a simple cubic? I mean, it's called what? First one, normal, all the corner lattice point. What is it called as? Oh, that is what it is. Okay, this is cubic, right? So under cubic, you have simple cubic, body-centered cubic, face-centered cubic, edge-centered.
Simple is only primitive, no sir?
Yeah, simple is only primitive. Yeah.
PCC something.
I think yes. I'm not sure. Right. So I'll tell you whatever these are. So in cubic shape itself, you can have 4 different possibilities of units. So again, edge-centered cubic we don't study. We study only the first 3.
Sir, hexagonal.
Right? Sorry, this hexagonal will come under different cubic system. That's what we can study hexagonal. But again, in this only edge-centered we'll study. But again, not much. No questions will come from this. Right? They will get questions only from cubic. But again, that is very complex also if you want to understand that. It will take a lot of time. But you will study cubic, simple, BCC and FCC. That you will study, and other systems. Anyways, so what I'm trying to tell you is cubic itself has a simple cubic body center. So like 4 things are there. Same way, hexagonal will have some other thing. Rhombohedral will have some number of things. Triclinic will have some number of things. So totally, if you put together all the unit cells together, right? So those unit cells put together what are called as Bravais lattices. So totally you can have 14 Bravais lattices possible. So 7 crystal, this can be a question also. So there are 7 crystal systems and 14 Bravais lattices. Right? Say body-centered hexagonal, face-centered hexagonal, body-centered say triclinic, something like that, some combination. Right? So like that, they can have 14 like proven configurations. 14 lattices are possible. Okay, right? So these are the basics which you have to know, right? And obviously, for simple cubic, body-centered cubic, and face-centered cubic, you need to know where are all the lattice points, and you have to know their packing efficiency, right? So, like, I think you should be knowing it. Where are the lattice points? Right? You know that, right? Where are the lattice points for simple? Right? So basically, simple cubic will have all the corners only to have a lattice point. Right. So okay. First, wait. what and all you need to know is what I'm telling, right? For any unit cell, right? First, you need to know where are the lattice points, right? Second thing is how number of atoms per unit cell, right? And not the number actually, but you, if you can remember, okay, relationship between R and A. You know what is R and A? A is the edge length of the cube. R is the radius of the sphere. Right? You'll use it. You'll use R and A for derivation of your packing efficiencies. Right? Fine. So these three things you have to know, and you know, maybe you remember what is the packing efficiency also. Okay. So for all the three cells, FCC, BCC, and simple cubic, you need to know all of these. Okay, right. So, like for example, if I take simple cubic, we know where are all the lattice points. At all the 8 corners of the cube, you have lattice points, right? And you know each lattice, from each lattice point, you can draw 8 different cubes from one point, one edge. I can draw 8 different cubes. So basically, that is shared by 8 other unit cells. That particular point. So the contribution would be 1 by 8 to that particular unit cell, right? And you'll see that there are eight such cases. So 1 by 8 into 8 will become 1 atom per unit cell. That is for simple cubic. And relationships, you know, right? So for, I think, R is equal to A by 2. Is it correct for simple cubic? Is R is equal to A by 2? For simple cubic? Great. Okay, maybe we'll check that, no issues. Okay, so you have to know this, right? It's fine. Okay, maybe we'll just write the unit cells, R and A relationship, and what else? The number of atoms per unit cell. Right, okay. So if I take simple cubic, R and A, okay, wait, actually, let me check, it's better. Really inorganic, right? Okay, guys, just give me a moment. Oh, something came. What is it? A is equal to 2R. Okay. Yeah, fine. Maybe if you just give me that, it'll be fine. Right. So A is equal to 2R. So what I wrote was correct then. R is equal to A by 2. Okay, fine. So A is equal to 2R and number of atoms per unit cell is 1. Right. And if you go for BCC, BCC number of atoms per unit cell is 2. Right. And then I think this is R is equal to √3 by 4A. Is it correct? R is equal to √3 by 4A is correct for BCC. Please check. Okay. And for FCC, and okay, FCC for face centered cubic, R is equal to A by 2 √2. I think I'm right. And the number of atoms.
Yes, sir.
Okay. So these things you have to know. Right. Okay. So this, if you know, what other things you need to know? Packing efficiency. Obviously, you see the packing efficiency of FCC is greater than BCC, which is greater than simple cubic. So this is around 54%, if I'm not sure, and this is around 68%, and this is around some 70s, right? Some 70 odd percentage, 74 if I'm not sure, right? So anyway, so you have to remember the packing efficiency. Not exactly the numbers, at least you need to know which is very close, which is having the maximum packing efficiency, that is FCC. That at least you need to know, and which is the least, which is having the least packing efficiency, that is simple cubic. That you need to know for problem solving. Okay, right? And one more thing also you need, that is about octahedral and tetrahedral voids. Okay, now please understand, people, right? If you have n number of tetrahedral voids, no, if you have n number of octahedral voids, you will have 2n number of tetrahedral voids, or I can write it like this: Nt is equal to 2 into No. Am I right? No. No, right? Number of octahedral voids is equal to 2 into number of tetrahedral voids. And what you have to understand is number of tetrahedral voids is equal to number of atoms per unit cell. Okay, so these two things you have to know for problem solving. Okay, so number of octahedral voids is equal to 2 into number of tetra, which makes sense, right? Because tetra means 4, octa means 8, right? Fine. So number of octahedral voids is 2 into the number of tetrahedral voids. And how will you find the number of tetrahedral voids? Number of tetrahedral voids for a particular unit cell is constant. That is equal to number of atoms per unit cell. So you can understand, for simple cubic, the number of tetrahedral voids is 1. For BCC, the number of tetrahedral voids is 2. For FCC, the number of tetrahedral voids is 4. Okay, so these things you have to know. And there is one more formula which you have to know, that is density formula. It's again a simple formula: Zm by Na into Aq. Okay, where Z is the number of atoms per unit cell. For again, these are constant for a particular unit cell, and M is the molar mass. Na is the Avogadro number, that is 6 into 10 to the power 23 approximately, and A is the side length. A is the side length. Cool, right? I think that's what you need to know. Other than that, everything is okay. Nt is equal to 2 into number of tetrahedral voids. Is it like that?
Yes, sir. Actually, yeah, sir.
Oh, Nt is equal to, okay, man. Okay, fine. My bad. Right, fine. Thank you. Changed it. Okay, so 90 is the number of tetrahedral voids is equal to 2 into the number of octahedral voids. Okay, done. Right, so these three things, these are all things, if you know, we can directly move on to problem solving. We'll just have to do a couple of problems because problems are less from this chapter. And yeah, the problems, one thing which is not there and you have to know is Bragg's equation. Okay, so what is this Bragg's equation is, you have something called as X-ray crystallography. You really need to, that's again a different field for itself, right? So basically, X-ray crystallography is used the method for determining crystal structures. Okay, so you pass X-rays to the particular crystal, right? So basically, I want to understand what is the bond length, or say what is the distance between two layers of atoms, something like that. Something for that, those things only X-ray crystallography is used. So basically, when I pass X-rays onto the crystals, right, and they will hit something and come back, right? So based on how much time the X-rays takes to come back, depending on that, the distance are calculated using your kinetics, right? So anyways, we don't have to go into details, right? So basically, how are you going to find the distance is governed by this formula called Bragg's equation. There are easy derivations for this. You can just go to the YouTube. You'll be able to get the derivation out. Pretty simple derivation. You don't have to worry about the derivation. You just have to know what is the equation. So it's equal to n lambda is equal to 2d sine theta. Okay, this d is what is the distance of separation, right? And basically, what you have to understand is these are you have studied diffraction, right? Basically, it's a diffraction technique, X-ray diffraction. X-ray crystallography can also be called as X-ray diffraction technique, right? Did you study this in physics? This same equation in diffraction?
No, sir. He didn't take ray of X-ray. No, ray and wave. He didn't take X-ray.
No, in your school at least,
No,
did you
sir.
see
No,
this?
sir. No, sir.
Okay, fine. Maybe this is actually in the normal diffraction. Maybe this is the formula you have seen. Harish says yes. Okay, so
sir,
usually
it's for us. It's like sin theta is equal to n lambda by 2d. I think so.
Exactly, something like that, right? That's actually Bragg's equation, right? So that is basically your diffraction equation, right? So you know what is this, right? So n is basically the order of diffraction. Second, it can be a zeroth order diffraction. I really don't want to go into the mathematics for this, but if you're in, but again, if you want me, I can go some other day, right? So this is what is called as order of diffraction. I know this is my wavelength of the X-rays, right? And this theta is the angle which the X-ray makes, right? This is the angle which the X-ray makes. Okay, so based on this also problems can come. Okay, right? Fine. So now we'll move on to the problems. How much time is left? Okay, we have time. Okay. Okay, we'll start with a very simple formula. Okay. So there is a compound which is made up of elements A and B. Okay, there's a compound which is made up of elements A and B. Not in this world, obviously. We don't have any symbol named as A and B in some other planet, maybe. Okay. So, anyways, so A and B are the elements which are going to form a compound, and it is having a simple cubic structure. Simple cubic, right? And what is, or not, basically cubic structure, we'll not call it a simple cubic. It has a cubic structure, and what they say is A is at all the corners, right? And B is at the face centers, right? So B is at the A is present in all the corners, and B is present in the face centers. Okay. Now what I'm asking is, what is the formula of this compound? What is the chemical formula of this compound? Can you tell me? This is a very simple question.
Sir, A8B4.
Sorry.
A8B4, sir.
That's, what is the empirical formula then?
A4B3.
You said A4B8, correct?
A8B4, sir.
A8B4. So what will be the empirical formula then?
A4B3. Oh, sorry.
A2B.
A2B. Sorry.
Okay, fine.
Sorry. I meant 4, I meant 6 instead of 4, sir. Sorry.
Oh, okay, fine. We'll check. I'm not sure it is correct. Okay, we'll check this. Right. See. So A, first talking about the A, right? We'll see how many molecules of A is there. Right. So basically, there are 8 corners. Right. And A is there obviously, but only 1/8 of the contribution comes to this particular unit cell, right? So 1/8 of A into 1/8 of A into 8 corners will give me how many A's? Only one A, right? Okay. Now, if I go for the face centers where the B is present, so one face is combined with, basically shared with another unit cell. One face can be a common. This side one cube can come, and this side another cube can come. Correct, right? So basically, B, if B, basically there I have how many faces? 6 faces. Hope you understand. What is the face? Maybe if I take a room, top is one face, bottom is one face, that side is one face, this side is another face, that is this side. This side is one, this side is one. So totally 6 faces. That's what you'll have. Right. So in 6 faces, the contribution would be 1/2 of B from each face center. So basically into 6 will become 3. So 3B is what I'll have. Correct. So basically what do you see? I have ratio is to be 1:3. So obviously this thing is going to be A, B, 3 will be the ratios, will be the formula.
Sir, I always don't understand why you take 1/8 into A and 1/2 into B, sir.
That's what. So it's because, see, that's how we calculate packing efficiency also. Hope you remember. Right. So what do? We calculate, see what I say, we want to understand. Right. So this is one, this is, okay, let me draw. Okay. So I assume that an atom is present here at the corner. Okay. Now, please, it just isolate this point and make it here. Right. Now, please understand, from a particular point, maximum, you will be able to form 8 cubes, making this as one of the vertex. Okay, making this as one of the vertex, I could actually have 8 cubes. Right? 8 cubes again will have some lines common between the 8 cubes. Obviously, that is for sure. Right? But from this particular point, I can form 8 cubes if you can imagine. Right? So obviously, what do you mean? This particular atom is not only solely exclusively for this unit cell. This has been shared with 8 other unit cells, like a cube. Right? So that is why whatever atoms we have on the lattice point here on the corner, you take only 1/8 of that, because we calculate per unit cell. How many atoms per unit cell is what we're calculating. Right? So obviously I have 8 corners, but from each corner I get only contribution of 1/8. So that I have only 1 atom per unit cell. But if I go for face centers, right, you see, or you take this itself, like, I don't know, like you are able to see the wall behind the board, isn't it? There is a wall, right? The door, right? So behind that wall, basically I have another room, right? But what are you seeing here? That is one face. That face can be shared between 2 cubes. Basically 2 cubes means 2 unit cells, right? So that is why we put the contribution. If I have the face center is 1/2 per unit cell. For one unit cell, what is the contribution? 1/2. So if they say that B is there in the face center, so I take 1/2 of that, each contribution, and I have 6 such faces. So it will be 3B. Did you understand?
Oh, okay. So basically, you take how many cubes, or how many cubes it can share. That, for example, if it's a point, or if it's a face.
Correct.
How many cubes can
see? That's why when it is going to be body center, what I do? Body center, it is in the center of the cube. How can I have a cube inside a cube? That is not possible. So that time we take the entire contribution only to that unit cell if it is BCC.
Oh, so you, for example, if A is it the center?
Correct.
Means
correct. If A
you just
was
do directly
center,
into 8.
Exactly. There is, again, you'll get only 1A, but not with a different calculation. No other calculation. That's it. If it's body center, in the center of the body, 1A. That's it.
So 1A into 1, something like that.
1A into 1. Correct. Exactly. There is only one body center, and the entire contribution to that is to that unit cell only.
Okay, sir. Now I get it. Thanks, sir.
Okay. Right. So how we understood this is AB3. Fine. Okay. Next question. Next question is this. I have a graph between log of lambda and log of sine theta, right? And I have a line like this. And this area or this length, right? This length is 0.3010 angstrom units. Right? And this was drawn for a second order diffraction. Right? So from the graph, I need to know what is the D value. So the graph is between log of lambda and log of sine theta. They are given a graph. So basically this length is what is given here, some Armstrong units. And you're high onto, this is a second order diffraction. You have to find what is the distance of separation, D. So basically you have to use that equation, Bragg's equation. And from the question, you can see that you have to take log, and they're given that it is going to be a second order diffraction.
Sir, I'm getting 0.3010 by sine theta, sir. I don't know how do you.
Okay, right. Fine. So if you take n lambda, or in this case, it's a second order diffraction. So let me take 2 lambda is equal to 2d sine theta, right? So sine theta, right? So 2 gets cancelled. So what you have is basically lambda is equal to d sine theta, right? So if I take log on both sides, what will I get? Log of lambda is equal to log d plus log of sine theta, right? So what do you have? This is x. This is sorry. This is y. This is x. So obviously the m is 1, right? So now what is this? This is the intercept C.
Oh, is it 0,
Correct.
sir?
How is it 0? Well, this value is what is my intercept. So this value is what is my log D. Is it not? Right? This value here, that is the intercept. And that value is what is my log D. Right? And that value is what is given here, 0.3010. Right? So basically what I understand from the graph, log of D is basically 0.3010. So what would have been the D value? Log of dash is 0.3010. How much? Log 2, right? So basically D is equal to 2 angstrom units. That's the answer to this question. Very simple thing, right? If they're given second order diffraction, you make the straight line equation, and you just apply the mathematics. There's no chemistry involved here actually. This is just pure mathematics, right? You just have to know what is the intercept, what's the slope. If you know that, calculate. That's it. Excuse me. Right? Next question, we'll go. Okay. Right. Take to the question. An oxide of cobalt crystallizes. An oxide of cobalt crystallizes with cobalt atoms occupying 1/8 of tetrahedral voids. Cobalt atoms occupying 1/8 of tetrahedral voids and 1/2 of octahedral voids right? So 1/8 of tetrahedral voids and 1/2 of octahedral voids in a closest packed array. In a closest packed array of oxide ions. In a closest packed array of oxide ions. Okay, I'll repeat the question. Right. So an oxide of cobalt crystallizes with cobalt atoms occupying 1/8 of tetrahedral voids and 1/2 of octahedral voids. Right. In a closest packed array of oxide ions. Okay. So I want to know what is the formula of the oxide cobalt. What is the formula of the cobalt oxide?
Sir, 1/2 means 1/2 or just 1/2, sir?
1/2 means 1/2.
Okay, sir. Sir, is it CO5O8?
No, see. Okay, first, when I say closest packed crystal lattice, what will come to your mind? What should come? Which unit cell should come to your mind when I say closest packed?
CCP.
Sorry,
CCP, sir.
FCC. Okay, fine, right. So it should be FCC which comes to your mind, right? So if we are going to have FCC, so I want if you just understand the statement, closest packed array of oxide ions. That means what? Oxide ions are there in a closest packed system. Array is a system basically, right? Closest packed system. So what you have to understand is all the O2 minus ions or oxygen atoms, however you want to call it, is entirely present in an FCC unit cell. That's what you need to understand. Okay. So in all the lattice points of an FCC unit cell, you have oxide ions present. Yes. Okay. So if that's the case, how many O2 minus will be there? Tell me. I'm telling you, in FCC, all the lattice points are occupied by oxygen. How many oxygen atoms? 3. Oh yeah, 3 only, no? Yes. 3. Okay. Right. Now, next thing is, next you have to go about all about the cobalt atoms. Now, how is it 3? Hope you understand. 1 by 8 into 8 is 1 plus 1 by 2 into 2. 1 by 2 into 6. Oh, no, it should be 4, isn't it? How? 1 by 8 into 8 is 1. That is for the corners. And 1 by 2 into 6 will become 3. 6 spaces. Contribution 1 by 2, totally 4 atoms. So the oxygen atoms will be 4, not 3. Right? Okay, so that's about oxygen atoms. Right. Next, if I go for cobalt, now they're talking about octahedral and tetrahedral voids. I told you the number of atoms is equal to the number of octahedral voids. Okay. The number of atoms is equal to the number of octahedral voids, and number of tetrahedral voids is 2 into the number of octahedral voids. This you have to understand. Right. So first what you have to understand is number of octahedral voids is 4, because that is equal to the number of atoms per unit cell. That I know in FCC lattice it is going to be 4. Right. So now what they're telling is octahedral voids, 1/2 of octahedral voids is occupied by cobalt atoms. So totally I have 4. 1/2 of this will be 2. So for now I have 2 cobalt atoms. I hope everybody understood what I'm doing here. I have 4 octahedral voids. The question says cobalt atom occupies 1/2 of the octahedral voids. So the 1/2 of 4 will become 2. Not only that, it is also occupying 1 by 8 of total tetrahedral voids. So basically I have to know first what is the total number of tetrahedral voids. Total number of tetrahedral voids would be 8, because 2 into 4. Right? Now in this, only 1 by 8 of this tetrahedral voids are occupied by cobalt. So what will be there? So I'll have 1 cobalt from this. Right? So totally how many cobalts? Totally you have 3 cobalts. So 3 cobalts, and you have how many? 4 oxygen atoms. So it should be what? CO3, O4 would have been the answer. Okay, CO3, O4 would have been the answer. Yes, I hope everybody understood what happened here. How I got 2 cobalt atoms, 1/2 of octahedral voids and 1/8 of tetrahedral voids. So that's what I did. So I got the formula as CO3O4. Okay, right? Fine. Next question. A similar kind of question we'll do. Okay, so I think this will be fine. So next question, they say CSCl, cesium chloride, right? So what happens is in this, CS plus ions is at the center of the cube, and Cl minus ions are at the corners. Okay, so CS plus ions is in the center of the cube, and Cl minus ions are at the corners, right? Okay, next thing is they have given a radius of cesium plus ion is 169 picometers, and that of radius of Cl minus ion is 181 picometer. right? So what I want to know is the edge length of the unit cell. Basically, edge length means what? A is what I need to find, right? Right. Now, maybe you will be wondering, sir, what am I going to do with the radius of the cation and the radius of the anion? Right. Now, please understand the radius of the sphere, the r which we speak about generally, right? That radius is equal to radius of the cation plus radius of the anion divided by 2. You always take this average. Okay. So whatever be the type of problem, right? You will take the average of the cation's radius and the anion's radius, and you get the radius of the sphere. Okay, right? So that's what is given. So now you know R of cation, R of anion. So you know what is the R value. And from this information, you have to decide what kind of unit cell it is. And you have to use that particular relationship to find what is the A. 1 second, please. Right? First, tell me from the information given, what type of unit cell is it?
BCC.
BCC, isn't it? So they say that CS plus is the center of the cube and CL minus is the corner. So you know this is definitely going to be a BCC lattice. Okay. So for BCC lattice, what is the relationship between A and R?
R is equal to root 3 by 4 into A.
Yeah, R is equal to root 3 by 4 into A. So R value we know, we'll be able to calculate, right? So basically you have to know A is equal to 4 by root 3 into R. And R value would be 169, 170, 250, 350. 350 divided by 2. 350 divided by 2 would be 150, 175. Right? So 175 is what is the R value. So 4 by root 3 into 175 is what you have to find. Root 3 value, you can put it as 1.73. And you can do the calculation. You'll get the answer. Okay, right? So whenever they give you radius of cation, radius of anion, do not get panicked. That's why I gave you this question. You just have to take the average of them and find the radius. 404.6. Yeah, 404.
Yes, sir, 404.
Okay, fine, correct. Okay, so maybe we'll just do one last question. Yeah, and then we'll wind up, right? And obviously, see, the same kind of question I would have asked you what is the, now along with edge length, I would have asked you what is the density for the same question. Now, what do you have to do at that time? You have to use the formula D is equal to Zm by NaAq. Correct. You know what is the molecular mass of cesium fluoride. You know now from this R calculation, you would have known what is the A value. Substituted in that equation, D equation, and you know what is the number of atoms per unit cell for BCC, that is 2. Right? So you would have used Zm by NaAq formula for finding the density. With the same information, nothing else. Instead of asking edge length, I would have asked you what is the density. Right? At that time, you have to find A first and then find the D value. Okay, right. Next question is, I have a compound having the formula AB2. Excuse me. Right. So I have a compound mineral having a formula AB2, which crystallizes in cubic closest packed lattice, right, where A occupying all lattice points. Okay, and you have, okay, B occupying some of the tetrahedral voids. Okay, you have, they're asking you, I mean, they're telling you B occupies tetrahedral voids, but they didn't tell you how much. Some of the tetrahedral voids. Right? Now, what I want to know is, what is the fraction of tetrahedral voids occupied by B, obviously, right? What is the fraction? Or I can just tell, if I just multiply this fraction into 100, basically I'm going to get the percentage, right? So you can even tell me what is the percentage of tetrahedral voids occupied by B.
%25, sir.
25%. Okay, we don't know. We'll check. Right. So now again, they have given cubic closed packed lattice. So this again tells you it is going to be FCC. There's no doubt about it. Right. Okay. Now they're telling that A is occupying all of the lattice points. So I know there is going to be actually 4 A's, because I know number of atoms per unit cell in a FCC is 4. Okay. Right. So if now obviously B, they're telling that B is there only tetrahedral voids. Right. So I know number of tetrahedral voids in a FCC would be 8. Correct. Right. So now what you have to understand is, if I look at the formula, I have A is to B is basically 1 is to 2. Right. So if I have 4 A's, how many B's I should have?
8, sir.
8 B's. Right. So I should have 8 B's. That means what? All the 8 tetrahedral voids are actually occupied by B. That's what you understand, right? So what is the fraction occupied by this thing, or percentage? Percentage is 100%.
Sir, I thought by lattice points, I thought it meant the corners, sir.
No. When I say the closest packed lattice points means all the lattice points, not only corners. They'll then specify at the corner. They'll specify. If they generally tell lattice point, and if they tell you what type of lattice it is, all the lattice points you have to take. Body centered means in the center of the body you have to take. Face centered means the face you have to take 6. Like that you have to do. Right? Okay. So pretty simple, isn't it? I got number of atoms of A as 4. So according to the formula, the number of atoms of B should be 8. And they say that B is there in the tetrahedral voids. So there are 8 tetrahedral voids, and all of them should be occupied by B. So the percentage occupancy is 100%. Okay, or the fraction is 1. Right? So yes, that's it. These are the type of questions you'll be getting, and obviously something related to some theoretical questions can come from, what is that? Why imperfections or defects in crystals, basically, right? So that part alone you read from the NCERT proper. You just read it and you get to know what is that. And if you have any doubts, you can ask me. I'll explain. And that's not a very big deal. That's an easy thing on you. Or if you're interested, maybe I'll teach you also. Was that part included in solid state for your boards? Defects in crystals?
Yes, sir. Included.
Included. Okay, fine. So maybe then it should be fine. So if not, just read about it. Ask me your doubts. I'll be able to help. Okay. So tomorrow's class, I think I'll be completing. Right. I told you only one chapter is left. That is amines. Okay. So please go through your NCERT and come, and tell your friends also, if they are attending the classes too, go through the NCERT textbook and come, and whatever reactions are not there, I'll teach it, and then we'll go for some problem solving directly. And with tomorrow, 99% would be the last class. Okay, fine. What is the time? I can leave almost 7 minutes. So you can go. Right. Thank you, guys. We'll meet again tomorrow.
Thank you, sir.
Yeah. Thank you, sir.